Hello, everybody. I hope you can all hear me. I will appreciate if you can give us a sign that you can hear us on the webinar. Okay, so my name is Yvette and I'm the marketing manager of Topo Storage. Today we will host the webinar Achieving the Ultimate Performance with KVM, and we have our Chief Product Officer, Bojan Krosnov, as a speaker. Just a few organizational things in the beginning. I will kindly ask you, all of you, to mute your microphones during the webinar. At any moment during the event, you can write your questions on the chat window, and we will try to reply them as soon as possible. At the end of the webinar, we will have a session with questions and answers, so everybody who wants can unmute himself at the end of the webinar and ask the questions. And today's webinar will be approximately 40 to 45 minutes with 15 to 20 minutes questions and answer session at the end. So now I'll give the word to Bojan Krosnov, and have a nice webinar.
Hi everyone. So this topic, achieving the ultimate performance with KVM, I've presented at a couple of conferences. It seems to be very popular. There is a lot of interest in this, which leads me to believe that like when people tell me performance doesn't matter, it's actually not true, because everyone that comes to these sessions is actually very interested in how to get better performance. So who is Topo and who am I? We've been doing high performance block storage since 2011, and Topo is kind of a good choice when you're doing for software-defined storage for virtual machines and containers. We're based in Sofia, Bulgaria. It's used mostly for virtual disks for KVM virtual machines, but it's also used for bare metal Linux hosts and also with VMware and Hyper-V more rarely. And we have deep integrations into OpenStack and OpenStack Cinder and Kubernetes and CloudStack and OpenNebula and ONAP and all these. Yeah, I mean, it's a kind of a scale-out, highly available, API-controlled block storage system. Right. So why performance matters? I think for the following reasons. One is for better application performance, because no one uses the kinds of systems we're discussing here in isolation, just for the fun of it. Everyone has kind of a business objective that they're trying to achieve. And application performance may be things like the time it takes for a web page to load, say in a web shop or e-commerce site, for example, the time it takes to rebuild or to run the tests in a testing and development environment, the time to execute a specific query in a kind of a analytics or batch processing environment, for example. For public clouds, it's also because better performance means happier customers. And for the kind of chief financial officer, the most important reason you want higher performance is to get better return on investment or better lower total cost of ownership. And this is achieved through higher performance, therefore higher density and a better consolidation factor, right? So there are multiple reasons why you want performance, and depending on kind of your goals, you may need performance because of one of these, right? One thing we did, so when exploring performance, one thing we like to look at is application performance. In this case, how does a transactional database perform on top of various public cloud services? And this is, you get very different results, even though if you're reading the data sheet of these virtual machines and these storage services, they seem very similar to each other, right? And on one of these services, you could get, say, 3,000 transactions per second. On another of these services, you could get 8,000 transactions per second, even though they, on the surface, they seem very similar. And I'll explain why this is further on in the talk. All right, so how do you achieve the best performance in a KVM-based public or private cloud? You need to, so there are multiple aspects to this. There is not a single knob that you turn to 11 and you get the best performance, right? So you need to look at your hardware platform, the KVM compute, CPU and memory part, networking performance, as well as storage performance. And when you combine all these, you get kind of good overall application performance, right? So in terms of hardware, we've seen generally there are two typical optimization goals. The usual optimization goal is that our customer, Storpo's customer, wants to achieve the lowest cost per delivered resource, say the lowest cost per VM, or the lowest cost per application running at a particular performance target. Right. So one kind of very common mistake in this is that sometimes people forget to include all the costs. So when you're talking about achieving the lowest cost per delivered resource, one thing you need to keep in mind is you need to include the cost of power and cooling and rack space and the cost of the server and the network and the cost of support and maintenance. And if you exclude some of these factors, you would be optimizing for the wrong thing. Right? All right. So in a more unusual case, the goal of our customer is to achieve the best possible single thread performance that they can get at any cost. And this is usually in some kind of, for example, algorithmic trading, machine trading on some financial markets and things like that. Very commonly, so in public cloud, private cloud, the optimization goal is getting the lowest resource, lowest cost per delivered resource, and the resource may be like a VM with 4 dedicated cores and 16 gigs of RAM. Right? So to achieve this, there is the way you achieve this. So the way you factor all these into account, so the cost of power, etc., is you build these Excel spreadsheets with hundreds of columns, and you punch in your assumptions like the power cost and the rack space cost and things like that, and it tells you kind of the total cost per gigahertz or the total cost per core given these inputs. And if you change the inputs, you obviously get different optimal hardware solutions. In this case, the choice of the CPU. Right. This spreadsheet we can share with anyone interested. Just drop us an email and we'll give you a link to the spreadsheet. Okay. And so for some of the typical parameters, the CPU models that come on top are things like these CPUs from Intel or these CPUs from AMD. And again, if you change the input parameters in terms of, for example, rack, power density per rack and things like that, your best CPU choice changes, right? So this is an optimization exercise, and the input parameters matter a lot in this exercise. Same goes for the compute platform, so the server. It may be in certain situations using a low-cost 2-rack unit server is better than using a density optimized 4 nodes in 2-rack unit chassis. So the server on the right is about 4 times denser than the server on the left. And which one is optimal depends on input parameters, right? So you can't recommend one over the other as a general rule, right? Other things that matter in terms of kind of hardware platform, firmware versions and BIOS settings, especially when it comes to power management and performance bias, and it's also very different. Kind of the recommended or best settings for this are very different on Intel's platform and on AMD's platform. So on AMD, there are kind of the 2 general modes are power deterministic and performance deterministic, while on the Intel platform, it's configured through C states and P states, and it's a different thing. And lastly, when you're optimizing hardware, it's very important to think at rack level optimization instead of kind of the cost of an individual component. So for example, the most optimal CPU models, they tend to be CPUs which cost $3,000. So if you're looking at only the cost of the CPU, you would never think that a $3,000 CPU is the most optimal, but when you run the numbers, it ends up being the $3,000 CPU, right? So this was on hardware. Moving on to KVM compute CPU and memory. Kind of a good starting point about this, about optimizing the compute part, the CPU and memory part of KVM, would be to look at these links, especially the first one. And very important here is do not apply blindly any configuration or tweak or optimization. Always when you're optimizing, when you're tweaking different settings for improving performance, you should perform benchmarking. Ideally, this should be application benchmarking. Ideally, this should be something that simulates your workload, not with a synthetic tool, but with the actual workload, right? So for example, if you're doing a development and test environment, you should be doing builds and tests and not synthetic benchmarks, right? So what you care about in application performance, for example, if you care how much time does it take to build, you should measure how much time it takes to build, not something completely unrelated, right? So that's a good start. And sorry about this. All right, so starting with which version of software you should use. You need a fairly recent Linux kernel and a version of the QEMU package, but obviously don't go to the bleeding edge upstream version, because that tends to have more bugs. The reason it has more bugs is not on purpose, obviously. It's because the upstream Linux kernel has not been tested by as many people as distribution kernels have. So for example, in our opinion, a good choice for this would be to use the QEMU KVM EV package for CentOS 7 or use Ubuntu LTS, and the vast majority of Storpos customers use one of these, either the Ubuntu LTS kernels and QEMU, or QEMU KVM EV from CentOS 7. A good starting point in terms of configuring the host is to use tuned, and there is a profile called virtual host, which does most of what's described in the articles. I had links to a couple of slides back, right? But it's not everything. There's always some other stuff that needs to be done. For CPU, there are two different ways of thinking about this. The more typical way is to have CPU over subscription, and the reason you want that is for better packing of virtual machines, because most you don't have VMs running at 100% CPU. They're mostly idling, so you want to share the CPU cores between multiple virtual machines. Hyperthreading is usually used, and in terms of NUMA awareness, the ideal way of doing things would be to make sure that each virtual machine stays within a single NUMA node. However, there are some situations where you can't do that. For example, if the virtual machine is larger than one NUMA node. A NUMA node, kind of a typical dual-socket Intel server, would have two NUMA nodes. So this means that even though the physical server, say a physical server has 512 gigabytes of RAM, your largest virtual machine may be 240, 250 gigabytes because you want it to fit inside a single NUMA node, right? Other things you can do on CPU stuff is route interrupts of network NICs and storage adapters to a CPU core on the same NUMA node that these hardware components are on. And kind of in a different approach, the more unusual way of doing this would be with CPU pinning. So CPU pinning conflicts with CPU oversubscription. So it's they don't mix well together, meaning if you're pinning CPUs, you'll end up with usually in the usual use case, you'll end up with a lot of CPU resource, CPU cycles wasted because the virtual machines you're pinning there are idling. They're not using these CPU cycles all the time, right? One important thing to understand about CPU oversubscription is to make the understand the difference between oversubscription and congestion. So oversubscription by itself does not lead to bad user experience. It's congestion that leads to bad user experience. It's when the CPU, say for example, you have a simple example. One of your customers has a VM with a single vCPU. They will get a perfect user experience. So they'll get all of their CPU cycles when they need them. If this vCPU is scheduled on an idle processor, right? If it's scheduled on a, if it's trying to execute on a hardware thread which is busy, then it will wait for execution, and that leads to bad user experience. But if you're maintaining your kind of overall load of your hosts, this doesn't happen, meaning the scheduler can always start, run that vCPU on a free CPU core somewhere on the host, right? And kind of an interesting metric or an interesting statistic you can use for that is that the Linux kernel exposes scheduler statistics. In the scheduler statistics, it exports a scheduler waiting time, not to be confused with IO wait time. It's a different thing. And scheduler waiting time is the time spent waiting to run a task on a processor. And a very important thing to understand is you may have 20% CPU load with a very large waiting time. And the way that happens is 20%, but it's in short bursts. And during these bursts, there is a lot more demand than their physical processors to serve, right? Or alternatively, in the case of pinned processors, you may have 100% CPU load and no waiting time at all, right? So to control, to deliver good user experience, what you need to do is you need to measure CPU congestion, not just blindly apply an oversubscription factor. And this is how that looks like. So this is a screenshot from Topo's metric collection system. Although we deliver a storage system, one thing we collect from all the hosts under our management is CPU metrics. And this specific chart shows exactly that. It shows the scheduler waiting time total for every host, and it's scaled to the number of hardware cores or hardware threads available, meaning 100% means that all of the CPU cores are busy, and on top of that, there are as many tasks waiting for execution. In short, you want this metric to always be zero. Anything other than zero means your customers are seeing still time in their virtual machines, which is something you'd like to avoid, right? And in this, for example, you can see that every 5 minutes, there is kind of a synchronized burst on many of the hosts. The reason for this is some scheduled activity in the virtual machines. For example, it may be a cron job in hundreds or 1,000 virtual machines. So you see that as a CPU congestion on all of your hypervisors during this every 5 minutes for a few seconds, right? And this helps you understand kind of your actual CPU load and helps you manage your hosts so that your users get the best experience, right? And in terms of memory, kind of the typical goal, the typical way of doing this is with, in KVM at least, it's with dedicated memory, dedicated RAM, which means it allows you things like huge pages and transparent huge pages, and it allows you to do things like localizing NUMA for the virtual machine. And the more unusual case is with oversubscribed memory. In the KVM hypervisor, this is fairly unusual. And other things in this category, so if you're doing oversubscribed memory, is memory deduplication, which is done with a service called kernel same page merging KSM, or with the balloon driver in the guest, which is also extremely unusual. Most typically in KVM, your virtual machines would have dedicated RAM and oversubscribed CPU. But it depends on use case. So for particular applications, you may want a dedicated CPU, right? That would be more unusual. On to networking, things start to get more interesting here, I think. So you also have this choice in networking. I think similarly to the choice you have dedicated vCPUs or oversubscribed vCPUs. In networking, you could do virtualized networking, or you could do pass-through networking. All right, so virtualized networking means its benefits are you get networking features such as filters in the host, you get live migration of virtual machines, etc. So, and with pass-through networking, you don't get these benefits. With pass-through networking, you get the best speed possible, but you don't get any of the features, meaning no filters in the host, etc. No live migration, right? Virtualized networking in KVM is usually done using the VirtualNet driver in the guest. And there are two mechanisms for how to get the packets in and out of the guest, and I'll explain this in a second. And there are 2 or 3 popular ways of implementing virtualized networking in KVM. The most popular perhaps is Linux Bridge, and the less second, in second place there is Open vSwitch DPDK, and I have a slide on that, right? So pass-through networking, what is that and how does that work? That is a scheme, a design in which you pass hardware directly to the virtual machine. And that means you bypass the host operating system. So the host operating system has no control over the traffic that goes from the VM to the NIC, to the network interface card. If you do this, you can't do live migration, and you can't do anything in terms of, for example, firewalling the host in front of the virtual machine, because the host operating system doesn't see the traffic, right? The way this is achieved is with SRIOV, and so it's a feature of the network interface card as well as the hardware platform. So being able to virtualize the NIC and pass parts of the network interface cards to individual virtual machines, right? So if you need, for example, if you need 10 million packets per second delivered to a virtual machine, this is perhaps your best choice. But if your requirements are somewhere in the middle, meaning you would like some of the virtualized networking features as well as high performance, your best choice is something else, right? So on to virtualized networking, the way this has traditionally worked is using the kind of regular VirtIO, which is processed in the QEMU process in the host. And in terms, that's very expensive in terms of context switches, and especially since Spectre and Meltdown, the Spectre and Meltdown vulnerabilities and their mitigations, this is very expensive and has a huge CPU and CPU time and performance penalty. So kind of a user space process, goes to the guest kernel, goes to the host, then goes to the QEMU process. So these are kind of three context switches already. And then the QEMU process submits the packet using a syscall, right? So there are many back and forths to submit even a single packet to send out the network interface card. So this is kind of an in-between situation, and with Open vSwitch DPDK, using a mechanism called vhost user, you bypass going through the host kernel completely, meaning the guest kernel talks to a vhost process, which is the Open vSwitch DPDK process, which runs on a different CPU core. And this communication happens completely without going through the host kernel. So it's a kernel bypass for getting packets from the guest kernel to the Open vSwitch DPDK, and there is also kernel bypass from Open vSwitch DPDK to the network interface card, so it doesn't use the driver in the kernel, right? And with this scheme, you can do millions of packets per second delivered to a virtual machine. However, you still have virtualized networking. You can still do things like bridging and filters, etc., in the Open vSwitch DPDK process, right? So that's kind of bridging filters, overlay networks, any more advanced virtualized networking function, right? In terms of popularity, this would be kind of the second most popular way of doing virtualized networking in the Linux, in the KVM stack, and it's a good trade-off. So it's if you want certain features and you don't want to give up these features and you still want high performance, this is a kind of a good way to achieve that, to achieve good networking performance. And lastly, onto storage, which is our specialty, and we are on the leading edge of doing low latency, high performance storage for virtual machines. So we have some interesting things to share. Similarly to what we saw in networking, in storage, you have a similar trade-off between doing virtualized storage or doing hardware bypass. So if you're only interested in low latency and speed, the best way to achieve that is just pass a complete NVMe device to a virtual machine, and you'll get the lowest latency possible, right? However, if you're interested in high availability and the ability to live migrate the virtual machine, and you're also interested in some storage features such as thing provisioning and snapshots and backups and kind of storage-based backups and etc. So virtualized networking, storage, then full bypass is not a suitable approach. So by full bypass, we mean SRIOV for NVMe devices. And if you're doing virtualized storage, you have the following kind of things to configure. So you should bypass the buffer cache in the host kernel by using direct IO instead of buffered IO, and this is using the cache equals known parameter of QEMU KVM. You should use Linux native AIO and not POSIX AIO, which is done with the IO equals native parameter of QEMU KVM. You could use VirtualBlock or VirtualSCSI. Generally speaking, VirtualSCSI is the better choice because it supports stream. VirtualBlock is also well supported, meaning it has the driver, etc., but it's not SCSI, so it's not a SCSI device, and it doesn't support certain features, for example, trim, right? In VirtualSCSI, there is another setting which is called multi-queue, which helps, and there is also another setting in QEMU which is called IO thread, not to be confused with IO equals thread. It's a different thing. So IO thread means that instead of the QEMU main process submitting the IO to the host kernel, there is a dedicated thread that does just that. So the QEMU main thread is free to do something else, right? again, similarly to how things happen in networking, in storage, the way a storage operation is submitted goes something like this. So you have the guest kernel goes to the host kernel, goes to QEMU. So that's VM exit, and then the QEMU process is executed, and then it goes again to the host kernel by doing a syscall, and then the host kernel talks to the storage system somehow over iSCSI or something else. And using the host user, you get the guest kernel talking directly to the storage system client, which is a process which runs on the hypervisor, right? So this gives you kind of kernel bypass between the guest kernel and the storage system, and this is available in Storpool and perhaps very hard to get anywhere else, right? Or impossible to get anywhere else. This is how kind of the architecture of a good storage system like Storpool looks like. So we apply the concept of host bypass or kernel bypass everywhere in the stack, which means that from the virtual machine, it can submit storage operations without going through the host kernel to a Storpool block process, which can submit storage operations or kind of can send and receive packets over the network, talking the Storpool protocol with kernel bypass, meaning it doesn't go through the host kernel, it talks directly to the network interface card. And on the server side, similarly, sending and receiving packets doesn't go through the storage nodes kernel, and sending and receiving storage operations to local NVMe drives doesn't go through the host kernel. It's directly between the Storpool server process and the NVMe drive, which means that in a Storpool storage system, end-to-end, there are no context switches to submit and complete storage operations, right? It's all done via a kind of a vhost or kernel bypass mechanism, or SRLV here and here, right? The other thing which kind of is important in this case, it's this architecture scales quite well, both inside the host. So if you need to have many NVMe drives inside one host, as well as across storage nodes. So across storage nodes, you can imagine you just repeat the same architecture inside of each hyperconverged or storage node. So it scales up in each storage node or hyperconverged, and it scales out to multiple nodes quite nicely, right? So on to how do you measure this stuff? First of all, beware of snake oil. So I think it's very important to stress when you're measuring performance, you should measure what you care about and not some synthetic metric. So if you care about, for example, how many mailboxes can I maintain on this mail server, just as a random example, this is exactly what you should measure: mailboxes on a mail server and not some synthetic metric, right? A lot of published performance benchmarks tend to be on hardware configurations which are unlike what you'd use in production. And they tend to be synthetic tests with very high I/O depth. And I'll explain why kind of storage system vendors do this in a second. And I'm saying here because why not? And the reason they do this is because this is the way they would get the highest, we call them hero numbers. So the highest IOPS number, even though it doesn't translate at all into application performance. And we've seen kind of really crazy stuff like they would show performance numbers with a RAM disk backend instead of a real hardware storage device. And lastly, synthetic workloads don't approximate the real workload. It's, I think, very important. Right, so something to understand about transaction processing systems, including storage systems, is that they have kind of IOPS or load versus latency characteristic that goes something like this. So at low load of the system, you will get the best service possible. If you increase the load, you would get slightly higher latency, and you would get to a point where you get the lowest cost per IOPS, or the lowest cost per delivered resource at a slightly higher latency, right? And then if you continue increasing the load, what you get is what we call only pain. So once you get over this knee in the curve, any additional load you put on the system the system would not deliver more. You will only get higher latency, you will not get higher throughput or higher IOPS numbers from the system. Unfortunately, most published benchmarks live in that part of the curve, meaning they put a large amount of load on the system to figure out how high this part of the curve is. And as long as this is high enough, you would be it's important that this is high enough, but it's not what really matters for application performance, right? So a more real example. So this was theoretically, this is how things should look like. In practice, if you measure it on a real system, it looks something like this. So as you increase IOPS, it tends to you get higher latency, and when you continue to increase load, you will get higher and higher latency, but not higher IOPS, right? So if you want a IOPS characteristic of a storage system, you would measure that part, right? And you would report that. And this way you can say this storage system can do 2 million IOPS, right? And that's something to be proud about, right? However, my question is, does changing that from 2 million to 2.5 million affect application performance in any way? And the usual answer is no, it doesn't. No, it doesn't change application performance in any way, because a real workload would live in that part of the curve. So moving that part of the curve up or down by 50% or 2 times wouldn't change application performance. What would change application performance is moving this part of the curve down. So getting to lower latency for realistic loads, right? Not higher IOPS numbers for unrealistic loads. And this has been our focus at Topo, because real applications live in this part of the curve. Getting this lower helps application performance. Getting the IOPS number higher doesn't really help application performance. So to reiterate, why we care about performance is because of better application performance and happier customers and lower TCO. And in this presentation, we had some guides, some ideas for how to achieve this better performance, both in terms of configuring the BIOS, the KVM hypervisor, networking in the KVM hypervisor, as well as in storage for KVM. This is all the slides I had. Thank you for listening in, and we are open to questions.
Yes, Boyan said, now is the time for the discussion and for the questions. I will start with 2 questions which we received during the webinar here on the chat. So the first question is, have you looked at adding EPIC-ROM chips to that spreadsheet? That's for the spreadsheet you showed.
Yeah, so the Xeon Scalable spreadsheet doesn't have EPIC-ROM on it yet. And it would be, I agree, it would be interesting to have the EPIC CPUs in the same spreadsheet, so we can do direct comparison between Intel and AMD, given when adjusting the input parameters, so see who does better at different input, power density, etc. parameters. We haven't done that yet. I think it's interesting, so we may do it. And as usual, the spreadsheet, it's not public yet, but anyone who asks about it, we will share it.
Yeah, the next question is actually in regards to the spreadsheet coming from our Facebook feed. Can you share a little bit more about the spreadsheet? What is the value inside, and is it possible to get it?
Yeah, sure. So just drop us an email. We'll share that spreadsheet with you. For whatever reason, we haven't made it public yet. But drop us an email, we'll share it, and it has in it their input parameters like cost for power, for energy, cost of rack space, cost of the different server components like memory modules and server chassis. It also, because it's for Intel Xeon Scalable, there are certain CPUs in there which only support single socket platforms and other CPUs that support dual socket and other that support 4-socket. It also selects the best single or dual or quad socket server platform depending on cost. So it will choose the best, it will choose to do it with single socket or dual socket depending on your input parameters. In most cases, it chooses dual socket except for the CPUs that are single socket. So it's fairly comprehensive as long as data center costs like rack space and power, networking like cost of the port on the switch, cost of the cable, and server hardware go. So cost of the server, is it better to do it with one rack unit servers or 2 rack unit servers? It covers all that.
Okay, thank you, Bojan. Going back to the spreadsheet, you can write us at info@storpool.com, so we will share the spreadsheet with everybody who is interested in it. And on the question if it's possible to download, view the slides, we will also send it to everybody who has registered for the webinar. If you are just logging directly the webinar and you're not sure whether you have registered or not, just email us again at info@storpool.com so that we can send you a recording of the webinar together with the slides. And we have 2-3 more questions. Before them, is there anybody in the webinar who wants to unmute himself and ask questions? Or I should continue with reading from the feed? No? Okay. So a question from Alex here on the chat. Other than presumably added setup complexity, do you see there being any particular downsides of going the route of OVS or similar for user mode network rather than handling it via the kernel?
All right, so what we've seen, one thing we've seen is orchestration systems like OpenNebula, OpenStack don't have exactly the same feature set in terms of configuring Linux kernel networking or Linux bridge versus configuring OVS DPDK. So they tend to have fewer features on OVS DPDK than they have on Linux bridge. Other than that, OVS DPDK obviously kind of takes a CPU thread. So there is one CPU thread which you need to dedicate to running OVS. In my opinion, and this is also our approach for doing virtualized storage, in our opinion, that CPU thread is well worth it, meaning you will get, with OVS DPDK, you can deliver millions of packets per second to a single virtual machine, right? And with kernel networking, there is just no way to achieve anything close to that. So in my opinion, it's very much worth it. And the drawbacks are you need to dedicate the CPU core, and there may be some features in your orchestration system which are not as well developed for OVS DPDK as they are for Linux Bridge.
Another question on the same topic. Do most of those features exist in OVS despite not being exposed by some management systems? And Charlie is asking that he assumes it has filtering and rate limiting.
As far as I'm aware, it has everything, including filtering and rate limiting and everything. Similarly to a lot of other, I think, situations, some of these features exist in OVS, but are not exposed through the orchestration system. As far as I know, it has filtering and kind of overlay networks and everything else. But I'm not an expert in it, so it may, if you ask someone who's more of a specialist in it, they may be able to give a better answer to that.
Okay. In the beginning of the webinar, someone has asked if it's possible to get a guide how to install Topo and to brief look how it's working on their own hardware or environment. Yeah, you can actually jump on a demo of Topo. If you again write us to info@storpool.com, we will be more than happy to do a quick demo for you. And if you have a use case for storage, of course, you can also test Topo on your own hardware, but you need to get in touch with us so that we can understand a little bit more about your use case. And another question, Bojan, for you is, do you have any comparison in performance between VirtualBlock and VirtualSCSI?
VirtualBlock and VirtualSCSI, we've done a few. I don't have any kind of numbers directly to share. VirtualSCSI is just slightly slower, meaning slightly higher latency and slightly fewer IOPS. But in our opinion, it's well worth it, both in terms of compatibility, because with VirtualSCSI, what you get in the guest operating system is a SCSI disk. So especially for Windows, that's a big thing. Both in terms of compatibility and in terms of features. So VirtualSCSI supports Stream and VirtualBlock doesn't. At least not with kind of typical guest kernels. So there is a slight performance advantage for VirtualBlock, but in our opinion, it's worth going to VirtualSCSI because of its other advantages, non-performance advantages. Right.
Thank you, Bojan. And the final question from the feed is, what tools do you use to measure the CPU usage and congestion?
So we've, as part of Storpool's metric collection system, we also collect CPU statistics, and it's a kind of a probe or an agent which we've written, and it sends these metrics to an InfluxDB database, which is kind of a popular metrics collection database, and it's part of our service. We haven't spent the effort necessary to open source that tool, right? I know there may be people interested in that, but the way we look at it is the kernel scheduler exposes these statistics, and it's very easy to get these statistics. They're just a text file that the Linux kernel exposes. So we don't see why not anyone could collect these statistics. It's very easy to do, right?
Any other questions? You still have some final minutes to write your questions on the feed or to unmute yourself and ask the questions. If there are no more questions, let's say thank you to Bojan for the nice webinar and the detailed explanations. If any questions rise after the webinar, you can write us at info@storpool.com, and as we said, we will send you the slides and the presentation and the webinar recording. So thank you everybody for joining us today, and stay tuned for our future webinars. Have a nice day. Bye.
Thanks. Bye.